Hello and welcome. Welcome back, folks. Let's move on to the next chapter that we're studying, which is chapter 22, associated with Gauss's law. Now, Gauss's law is actually a very important concept. It will play out in just about every part of the rest of the course. That is why I would basically advise people to really pay attention and study Gauss's law properly. So let's go ahead and study Gauss's law. The thing to point out is that Gauss's law is an alternative procedure for evaluating electric fields. And we're going to actually go ahead and come towards Gauss's law in slow stages. So we'll have a very extensive introduction, which kind of serves to set the stage for our study of Gauss's law. And then we'll go ahead and study Gauss's law in great detail. Now, you must have noticed when studying Coulomb's law that the force between two charges varies inversely as the square of the distance between the two charges. That is to say, the distance, it's always the distance raised to a power of 2. It's never a distance raised to a power of 1.99 or the distance raised to a power of 2.01 or 2.0001. So you realize that there is something very special about this denominator that we had in Coulomb's law, and Gauss's law essentially builds on that insight. It is very convenient to use Gauss's law, especially when you have symmetric charge distributions. So we will actually go through a plethora of examples to show that whenever you have a symmetric charge distribution, Gauss's law is in some sense the preferred way of evaluating the charge out there. We will also go ahead and show that there are various little properties associated with Gauss's law that allow for Gauss's law to be used in a qualitative sense, even in situations where we're not using it to exactly evaluate the charge distribution. And nowhere is that more apparent as when studying the properties of charges as they distribute themselves on conductors, especially in a state of electrostatic equilibrium. So we'll go ahead and reinforce that. And I would point out that there's an interesting dichotomy between Gauss's law and Coulomb's law. They're both effectively equivalent, yet there are certain classes of problems that are solved very efficiently with Gauss's law and not so efficiently with Coulomb's law. Vice versa, there are other classes of problems where Coulomb's law takes front stage and Gauss's law is not a very efficient choice. So let's go ahead and in this chapter reinforce our notion of Gauss's law. Um, so we essentially can say, or we essentially recap from the last chapter, that we studied electric field lines and we understood that if you have a positive charge, then the electric field lines emanate outwards from that positive charge. Let's say you have twice of a certain positive charge, then we also understood that the number of field lines coming out of that larger charge would be twice as many. If you have a negative charge, we understood that the field lines go into the negative charge. If you have twice as much of a negative charge, you understand that you have twice as much of the field lines going into that negative charge. So we understand now that Gauss's law is one way of making that relationship between field lines and charges much more concrete and quantitative. So at a qualitative level, Gauss's law basically says something like this. Consider any closed system that encloses consider any closed surface that encloses some charges. Okay? The number of field lines leaving that surface is proportional to the amount of charge enclosed in that surface. In other words, if you have a net positive charge inside that surface, then there'll be a net positive number of field lines leaving that surface. If you have a net negative charge inside a closed surface, then you will have a net number of field lines entering that closed surface rather than leaving that closed surface. And we'll set up a convention which says that field lines entering a surface are to be counted negatively, field lines exiting a surface are to be counted positively. Now notice that you can only have this notion of entering or exiting if you have a closed surface. So one important thing about Gauss's law is that it always applies to closed surfaces. Okay, now understand that Gauss's law stated this way is very, very powerful because it basically says that it applies to any and all possible closed surfaces that you can imagine. So even if you have different closed surfaces, but they enclose the same set of charges, and some of the charges can be positive, some of the charges can be negative, and we'll see that reinforced in examples. Even if you have different closed surfaces that essentially enclose the same set of charges, then Gauss's law basically says that there's always the same number of field lines crossing those two closed surfaces. Now notice that there is a caveat all the way through, which basically says that Gauss's law can only be applied to closed surfaces. It cannot be applied to anything other than closed surfaces. And again, we'll have some qualitative analysis to reinforce this issue even in our introduction. So with that said, let's basically focus on this interesting thought question. It says that you have a charge plus Q as shown by the red charge out here, and you essentially have these four closed surfaces. So you have the spherical closed surface that is containing the charge Q. You have the orange closed surface, which also encloses the charge Q. And you have this, the purple and the green surfaces, that's surface 4 and surface 3. The question asked is, how many field lines, or what is true about the field lines that are coming out of this charge and passing through the surfaces? Now notice that you can answer this question at a very trivial level by essentially counting the field lines. So if we focus on the blue surface, the spherical surface, and the orange surface, the surface number 2, we realize that, first of all, there are, in fact, we can count it up, there are exactly 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, and 6 more, which is 12 field lines coming out of that surface. Okay, and notice that every field line, for example, this field line, if it cuts through this blue surface, it is also going to cut through the orange surface and in an outward direction. So we see that every field line that cuts through the blue surface can also be counted as positively cutting the orange surface. So that essentially begins to tell us that the number of field lines crossing surface 1 and surface 2 should in fact be equal. Now we've solved this part of the problem in an extraordinarily pedestrian way by essentially counting field lines. But it's also possible to solve it in a slightly sophisticated way by using our nascent knowledge of Gauss's law, where you realize, or you can argue, that the blue surface and the orange surface, namely surfaces 1 and 2, both enclose exactly the same point charge. And if they enclose the same point charge, then by Gauss's law, it is guaranteed that they have the same number of field lines coming through them. Okay, so we can actually say that the same number of field lines cross surfaces 1 and 2, either by simple brute force counting or alternatively by a somewhat more sophisticated application of Gauss's law. Now, as we go further, we will make our application of Gauss's law more sophisticated. Now, let's focus on surfaces 3 and 4. For example, let's focus on surface 4. Notice that for every field line that enters surface 4, the same field line actually exits surface 4. So you see that out here, the field line that enters it would be counted negatively, but that same field line exits it and therefore would be counted positively. Likewise, out here, the field line that enters it out here would be counted negatively, but the same field line exits it out here and is counted positively. Likewise, out here, the same field line that enters it out here is counted negatively, but it's the same field line exits it and is therefore counted positively. Therefore, we see that there's a one-to-one correspondence, namely count -1 for a field line entering, count +1 for a field line exiting, and therefore the net number of field lines crossing through surface 4 is exactly 0. You can make a similar kind of argument for surface 3. This right there tells us that the field lines through surfaces 3 and 4, the net field lines are exactly 0. Namely, they have the same number of field lines leaving them as entering them. Okay? Okay, so now that we have this notion, we can also have a more sophisticated way of thinking about surfaces 3 and 4 by basically saying that, look, surfaces 3 and 4 do not enclose any charge, and therefore, by Gauss's law, the net electric field lines, the net counting of electric field lines across those surfaces must in fact be exactly 0. So with that, we realize that D is the right choice for the answer. Okay, now that we've argued our way through this question, let's go ahead and focus on the next question. The next question basically shows a pair of equal charges. So both these two red charges are in fact equal, and we're asked to basically make similar statements as in the previous problem, but now concerning the blue surface, the green surface, and the purple surface. So now let's go ahead and ask, how many charges do we have inside the blue surface? And the answer is we have both the charges contained inside the blue surface. Likewise, we have both the charges contained inside the green surface. So that tells us that the number of field lines crossing surfaces 1 and 2 should in fact be the same. Now notice that both the charges are equal, and the purple surface encloses exactly half as much charge as the blue or green surface, which basically means that surface 3 has exactly half as many field lines crossing it as surfaces 1 and 2. So this is an example where we now no more need to count field lines, but rather essentially just use our conceptual understanding of Gauss's law to answer this problem. So with that, we basically realize that D is the right answer. Now, with that increase in sophistication, I'm sure that you guys will be able to answer this question, which deals with the fact that you have a dipole, namely equal and opposite charges, and a charge of plus q, that's the red one, and a charge of minus q, that's the blue one. And these two charges are separated by a certain distance. This is our definition, our textbook definition of a dipole. And then you're asked to make basic statements about surfaces 1, 2, 3, and 4 and identify the right answer. Okay, so go ahead and think about that, and maybe we can think about it again when we're in class. So we made a lot about there being closed surfaces and closed surfaces being the only types of surfaces that are acceptable. Let's go and reinforce that concept. So here you see essentially 4 figures, A, B, C, and D. And for each of those surfaces shown in A, B, C, and D, you are shown a normal vector which is either outward pointing or inward pointing or whatever. And I want you all to decide whether you can choose A or B or C or D or E. What do you think? Now, let's go ahead and identify that most students might in fact gravitate towards this answer. So they might actually say that for A, the normal vector is pointed outwards. For B, the normal vector is pointed inwards. For C, the normal vector is pointed outwards. That only makes sense because you might actually think of completing this surface and saying that indeed the normal vector is pointed outwards. And for D again, your natural instincts are to say that the normal vector is pointed inwards because again, the human brain wants to essentially complete the surface and say that indeed it is pointed inwards. But is that really true? Now look at this. I could actually complete this surface by drawing it like this, which actually makes the normal vector inward pointed rather than outward pointing. Okay, so this tells us that the normal point vector in this case has been made inward pointing, and therefore we realize that for surfaces that are not closed, we cannot identify an inward or outward pointing normal vector. Likewise, here too, notice that I could close the surface this way and throw your intuition to a loop because now the unit normal becomes outward pointing rather than inward pointing. So this tells us that in fact this is the right answer. So this tells you that you have to be careful because you can only have a notion of inward pointing normal vector or outward pointing normal vector if and only if the surface is closed. If the surface is not closed, then all bets are off and you have no right to say anything about that situation. Now let's go ahead and at least develop a slightly further qualitative understanding of flux. Okay, because this notion of a flux will play a very important role in the rest of our study in this chapter. So we can actually go ahead and say that imagine you have the city of Chicago to the left and you have the city of South Bend to the right. And this is I-80, which connects the two cities. Now in the morning, what do you expect? You expect that the flux of cars should be greater in the direction of the city of Chicago because people would want to kind of drive into the city of Chicago to do their work in the downtown area. In the evening, you expect the flux of cars to be in the opposite direction because people will be leaving their workplaces and going back to their homes, which are in the suburbs, and therefore you have a flux in the opposite direction. So this gives you your pedestrian notion of flux, namely your flux can be defined as the flux of cars on a highway, and in that case you would essentially say that it's the number of cars per unit area times the velocity of the cars. Now notice that you have to have a very accurate definition of the flux. For example, suppose I put this tape measure across the lanes of the highway. Then I can essentially go ahead and count the number of cars that are crossing from the right to the left in the morning, and I can identify that in the morning I have a flux of cars that are going from right to left across this tape measure. But I could also set up another tape measure nearby, which is this tape measure. The flux of cars that I measure across the oblique tape measure should in fact be exactly the same as the flux of cars across the straight tape measure. So this tells us that we have to have a notion of flux that is independent of the orientation of the surface through which we're trying to measure that flux. Now, we also have a notion of flux in other situations. We can say that the flux of water coming out of a faucet is strong or it's not strong, or so on and so forth. We also talk about things being in a state of flux, namely things being in a state of change. So this tells you that the notion of flux can that our notion of flux has to be properly defined in order for us to basically use it within the context of physics. And let us essentially, in the next section, develop this notion of flux. Now we're going to develop it within small gradual stages. So we're essentially going to say that imagine, if you like, the simplest situation where you have this area A and it is held exactly perpendicular to the electric field lines that you see in the figure. In that case, it becomes easy to quantify the number of electric field lines crossing through the area. You realize that it should be proportional to the electric field, or the strength of the electric field, times the area itself. Now notice that that naturally gives us our notion of flux because electric field has a notion of newtons per coulomb, or electric field has units of newtons per coulomb, and area has units of meters squared. So our units for our simple notional definition of flux is that flux is measured in Newton meters squared per coulomb. Okay, now that we have this notion, let's go ahead and extend it and mathematicalize it in the next transparency. So here we have a situation where we have, again, electric field lines, but we have two possible surfaces. We have the vertical surface, which is the surface shown out here, okay? And we have the oblique surface, which is this surface shown out here. Now notice that just based on scanning the figure, you realize that every electric field line that goes through the vertical surface actually, in fact, goes through the oblique surface too. So if you're thinking about flux as being a way of counting field lines, the two surfaces, the vertical one and the oblique one, should in fact have the same electric flux going through it. So we have our notional definition of electric flux as some way of counting the number of electric field lines flowing through an area. Okay? Now, for this vertical area, we realize that the angle between the oblique area and the vertical area is in fact this angle theta. And therefore, if the area of the oblique surface is A, then the area of the perpendicular surface is basically given by A cosine theta. So this tells you that if you want to measure the flux using your original notion of flux, you would essentially say that the flux, the electric flux phi E, is just equal to the electric field times A perpendicular, which you therefore simplify as E times A times cosine of theta. Now notice that you want the same answer even if you're considering the oblique area or the oblique surface, even though the oblique surface has a larger area. And this tells you, just by scanning this definition, this tells you that there's a cosine theta involved, which suggests to you that we've met this notion of a cosine theta before. Okay? If you have two vectors and you take their dot product, then that dot product will in fact be will in fact have a factor of cosine theta. So if we basically go ahead and develop some notion of a dot product, I think we will be home free in our definition of a flux. So how do we develop that concept? And the answer is that instead of thinking of area as being something that has units of meters squared, we think of area as being a vector. This vector, called the area, has a size that is exactly proportional to the area of the actual surface that you're considering. But it has a direction that is pointed in the normal direction to that surface. Now notice that any surface, if it's just an arbitrary plain sheet of paper, it will have two unit normals pointed in either direction. So to make this more specific, we'll have to go ahead and resort to our understanding of a closed surface, which we will develop very shortly. But this actually tells you that you can write this as E vector dotted with A vector, and then we have a perfectly good definition of flux, because notice that if we apply this definition to the larger oblique area, it returns the same value for the flux as if we apply to the smaller perpendicular area or the smaller vertical area out here. So this area out here and this area out here basically give us back the same answer for the flux, provided we have this notion that the electric flux is proportional to E vector dotted with A vector, and we promote the area, we promote our definition of area to be that of a vector. We will do that by basically focusing or latching on to the normal vector to that area, and we will go ahead and amplify this notion in the next few transparencies. Now notice that if this oblique area had been such that theta is exactly equal to 90 degrees, namely if this oblique area, if this surface, if this larger surface had been completely horizontal like so, if this surface had been horizontal like so, then you actually realize that the number of field lines crossing through it is exactly zero. And that is so because in that case, the normal to this surface that I have drawn would be like this, and the normal direction is perpendicular to the electric field direction. Therefore, cosine of 90 degrees is exactly zero. So the flux is zero when the surface is perpendicular to the direction of when the normal to the surface is perpendicular to the direction of the electric field. Then the flux is maximum when the surface is perpendicular to the field. In other words, when the unit normal or the normal associated with that area is exactly aligned with the electric field. Okay, so with this, we essentially go ahead and develop this concept even further. Now notice that very often, especially because this is a calculus-based course, we get down to calculus. Okay, so now let's go ahead and define the flux associated with some very curved, complicated area like the area shown out here. What you would do if you had to define the flux of electric field, as shown out here by the purple arrow or the red arrow, if you had to define the flux of electric field across this curved area, you would basically go ahead and split this curved area into little infinitesimal patches, and for each of these patches, you would essentially identify an outward pointing area like so. Okay, so you can identify an infinitesimal area where the outward pointing normal is perpendicular to the surface area, and you can also say that the length of this vector is proportional to the infinitesimal area that you're considering, and you can define the infinitesimal flux delta phi sub e as being equal to EI vector dotted with delta AI vector. Okay, so this is our vectorial definition of an infinitesimal flux. And if you want to go ahead and find the total flux, then you can actually go ahead and say that phi sub e is actually equal to the integral of EI vector dot delta AI vector, which basically says that split the entire surface up into small infinitesimal patches and then go ahead and evaluate the flux through each of those infinitesimal patches. And now that you know how to use integral calculus to evaluate infinitesimals, go ahead and put it all together as an integral, and you've got yourself a flux. So with this insight, we're ready to move forward. Notice that up to now, we have not been very specific about how to define an outward pointing normal, but that notion of outwardness or outward pointing normal is now very apparent if we consider this closed surface that is threaded through electric field lines. So notice that there are no charges in this figure that you're seeing at the right top, but you have this ellipsoidal surface that we've split up into many infinitesimal pieces. For example, this is the infinitesimal piece number 1, and we have magnified it out here. This is the infinitesimal piece number 2, and we have magnified it out here. This is the infinitesimal piece number 3, and we have again magnified it out here. Now notice that in each circumstance, because we're dealing with a closed surface, we can actually have a notion of an outward pointing unit normal. And for each closed surface, we have a distinct notion of inwardness and outwardness, and we essentially define our area for that, and we essentially define our area vector as being the area associated with the outward pointing normal. So we see that this outward pointing normal across surface 1, infinitesimal surface number 1, is in fact going in this direction, and the electric field is going in this direction, and the angle theta is an acute angle, and therefore we see that the amount of flux crossing through the infinitesimal patch number 1 shown in the figure is in fact positive. Now let's focus on the infinitesimal patch number 2. Now notice that the outward pointing normal is in this direction, and the electric field is in this direction, and the electric field and the outward pointing normal are in fact exactly perpendicular to each other. This tells us that the dot product of the two should be exactly 0, and that tells us that the electric flux through this area element is exactly 0. Now what about the area A3? What about the third area that we identified? Notice that for that area, the outward pointing normal is in this direction. However, the electric field is still in this direction, and therefore cosine theta will correspond to the cosine of an obtuse angle, and therefore the flux associated with that infinitesimal element is essentially negative. So this harkens back to the little exercise that we did out here in the thought question in the previous section, which basically reinforces the notion that you can only have the notion of an outward oriented normal if you're dealing with closed surfaces. And this explains why Gauss's law is so strict about only applying Gauss's law to closed surfaces. So when you apply Gauss's law, make sure that you're dealing with a closed surface. Okay? The next transparency just gives you a magnification of those areas so you can actually see them more thoroughly. And with that, let's go ahead and move on and define our notion of flux through a closed surface. So we've already seen that we can take E vector dotted with an infinitesimal area dA vector, and this gives us an infinitesimal amount of flux. But now across a closed surface, we can actually go ahead and write the area integral in this fashion. Why do we make that circle around the integral? The answer is we make that circle around the integral just to reinforce the notion that we're working with a closed surface, and we're doing this area integration over a closed surface, and that gives us the total flux, the total electric flux across that closed surface. So this definition is kind of very important. Understanding how to kind of roll it out is very desirable. So with this, we're now ready to go ahead and do a little bit of a example problem and then move on to the next section. So what is our example problem? Our example problem is that we focus on this cube. Notice that because the cube is closed, because the cube constitutes a closed surface, we can actually identify an outward pointing normal in the minus x direction on the rear face of the cube, and an outward pointing normal in the positive x direction on the forward face of the cube, namely the face that faces us. Likewise, on the top face of the cube, we can identify an outward pointing normal like so. On this face of the cube, we can again identify an outward pointing normal for the cube, which is actually pointed in the negative y direction. And we can do the same thing in the z direction, and those z directional areas are not shown out here. The question is, if you have a uniform electric field, then you realize that E vector dotted with dA vector is actually going to be a negative quantity, because dA vector and E vector are oppositely oriented, and therefore they will have a cosine of 180 degrees, which is -1. Therefore, you now understand that if the length of this cube, of the length of the sides of this cube is L, then L squared is the area associated with this face, and the electric flux going through this face is in fact negative. You can do the same game with this face out here and realize that now dA2 and E vector are aligned, namely cosine of theta is cosine of 0 degrees, and that is in fact equal to 1, and therefore for phase 2 you have a positive flux, and you can therefore say that because the electric field lines are straight, namely they're not beginning at some charge or ending at some charge, therefore the total flux through this surface is exactly 0. So this is like a nice little warm-up example to get us oriented. Now let's go ahead and move on and seriously define Gauss's law. So just to recap, Gauss's law at a qualitative level is an expression about the general relationship between the net electric flux through a closed surface and the charge enclosed within that closed surface. So we have a very specific name for such surfaces. We call them Gaussian surfaces because they're the surfaces that we use to solve our Gauss's law problems. So now let's go ahead and tack down Gauss's law in the simplest of contexts where we have studied the situation already. So now imagine that the charge Q is placed at the center of a sphere with a radius r. Then for this electric field that is crossing through the surface of the sphere, we can definitely say that that electric field is just equal to Coulomb's constant times the charge divided by radius squared. Now notice that delta A, the outward pointing the outward pointing area associated with this darker surface out here, delta A is also in the radial direction. Therefore, E vector dot delta A vector, so if we evaluate E vector dot delta A vector, that in fact will be just equal to E times delta A. So that tells us how to evaluate the electric flux through this darker shaded infinitesimal area that we're considering. And now let's go ahead and do the area over the closed surface of E vector dot dA vector. Notice that because the electric field is a constant at all points on this spherical surface, we can write this as integral of E times dA, and also notice that E and dA are aligned with each other, and therefore because the electric field is a constant, you can pull it out of the integral and you can write it as integral of dA. Of course, I have to remember that this is a closed surface, and that essentially says that our electric flux phi sub E in this situation is exactly equal to E times the integral of the area across the sphere, which is just given by E times 4 pi r squared. Now let's go ahead and write our electric flux phi sub E, which formally speaking is written as this integral E vector dot dA vector. And this is actually equal to the electric field which we've identified out here, which is just given by KQ divided by r squared times 4 pi r squared. Notice that r squared and r squared can quickly be cancelled. So we can write this as 4 pi k times q. What is 4 pi k? Recall from the previous chapter that we wrote k as being equal to 1 over 4 pi epsilon 0. Okay? Where epsilon 0 was the permittivity of free space. We will quantify it in the next transparency or two. So that tells us that k times 4 pi should be actually equal to 1 over epsilon 0. So this tells you that we can complete this equation by writing it as q divided by epsilon 0. Okay, so this gives us a nice notion of electric flux In other words, the purpose of this exercise is to actually quantify the proportionality constant associated with the flux. So with our definition of flux, we now understand that the total electric flux is equal to the charge inside divided by the permittivity of free space, epsilon naught. Okay? With this, we can essentially go ahead and identify or recap the different Gaussian surfaces. Again, you should be able to now understand that the surface S1, the surface S2, the surface S3 all have the same number of field lines crossing them, simply because, and therefore they have the same amount of flux crossing them, simply because they all enclose the same charge shown in this figure. Likewise, if you have a closed surface that lies outside, entirely outside, that does not contain the charge Q shown in this figure, then you should be able to understand that for each field line entering that closed surface, there's another corresponding field line leaving that closed surface. Therefore, the net number of field lines is exactly 0. So this allows us to come to our mathematical definition of Gauss's law, which basically says that you consider any closed surface. This surface is called a Gaussian surface, and evaluate the flux across the closed surface. Notice that the circle around the across the integral is basically meant to remind you that you're only considering closed surfaces. Then the electric flux across that closed surface is just equal to the charge inside, the total charge inside, divided by epsilon naught. Okay? And epsilon naught is just equal to 1 over 4 pi k, where k is Coulomb's constant. So you can stick Coulomb's constant in there, and you can get this value for epsilon naught. The units of epsilon naught are just reciprocal of the units for Coulomb's constant. So with this, we're ready to essentially close out this section after this transparency. And there's an interesting problem out here, which basically says that this charge Q is located at the center of this cube. The question asked of you is, find the total flux through the surface of the cube. That should be easy now, because if the cube constitutes a closed surface, which it does, and if it has a charge within it, then the answer to the first part is that Q over epsilon naught just gives you the electric flux phi sub E through the entire surface of the cube. Part 2 is kind of tricky, or at least slightly tricky. Notice that we are told that the charge Q is located smack dab at the center of the cube. This tells you that by symmetry, the amount of flux going through each face of the cube must be equal to the amount of flux going through each other face of the cube. So all 6 faces of the cube therefore have the same amount of flux going through them. And so the answer to the second part is that we take the flux that we got in the first part. So this is the answer to the first part. Now, the answer to the second part is that we take the flux that we got in the first part and just divide it by 6. So Q over 6 epsilon naught essentially gives us the flux through each face of the cube, through one face of the cube. Okay? So that's the answer to this problem, and we leave the next problem as a topic of discussion. So with this, I will essentially thank you for your attention. Thank you for learning about Gauss's law, and please use this to get a super good qualitative understanding of Gauss's law, because in the next unit, we're basically going to get extremely quantitative with Gauss's law. Physics is all about solving problems, and we're going to go ahead and make sure that you know your Gauss's law and how to solve Gauss's law problems forwards, backwards, upwards, downwards, and whichever other way you want. So with that, I'll thank you very much, and I'll hope to see you in the next unit. Thanks a lot. See you all then.